Hello, everybody, and welcome to the second session of PICMG's COM-HPC Mini Academy, which is aptly titled Introducing COM-HPC Mini. I'm your moderator, Lewis. I'm co-marketing officer at PICMG, and I'm joined by Richard Pino, who's a business development manager for modules at 80 Link Technology, and Chris Engels, who's a product marketing manager at Avnet Embedded. So for context, let's take a look back at what we discussed in the last session, which was essentially an update of everything that's happened in the COM-HPC ecosystem since it was introduced back in 2021. That includes exclusive support that Christian went through, a new connector that Matt talked about, PCIe Gen 6 compatibility, and of course, some foreshadowing into the new mini form factor. Now we're going to dive deeper into the electromechanical features of COM-HPC Mini and some application possibilities, which Chris is going to take us through. So this is session 2 of 4, and it's going to be approximately 25 minutes. We ran a little bit over in the last session, but we'll try and do some catch up here. After this, we're going to transition to session 3, where Peter Hunold is going to give an in-depth look at updates to the COM-HPC carrier design guide so that you can accelerate your designs with the Mini. And you'll want to be on the lookout for links in the chat and in over the screen to get you to that session. Once this session concludes, you'll also be redirected back to the event page. So you use a drop down there to select which event to show up to. So that'll be how you get into the subsequent sessions. So a quick reorientation of your viewing console. You use the large chat box on the far right of the viewing window to interact with other event attendees, type messages into the text box and hit enter, or you select the paper airplane icon with your cursor. That chat area is distinct from the questions tab, and you can navigate to the far right of the bottom menu to find that questions tab icon. Once you select that, it'll call up a new interface that prompts you to ask a new question. Click that, then the question once you click that, window will pop up and you can put your question in there and click send question. We'll get to as many of these as we can, not after this session, but in the fourth session of today, which is going to start around 15:30 UTC, when we'll have a panel of experts, including Christian Nader from Congatech, Matt Burns from Samtech, Pinner Hunold from Contron, and others joining us to take care of all your questions. However, if you have tech support questions, we'll get to those right away. So put those into the questions or questions tab or chat box, and we'll have one of our techs assist you as quickly as possible. You can also use the help button on the far left of the bottom of your menu to navigate, to get essentially a guide that'll walk you through how to resolve whatever issues you have. A final item of note is that all PICMG presentations are copyrighted and may not be recorded without prior permission. So now that we've got all that out of the way, I can hand it off to Richard, who's going to take us through some of the electromechanicals of COM-HPC Mini. Take it away, Richard.
Great. Thank you, Brandon, for the introduction. So today it's my pleasure to guide you through the key features of COM-HPC Mini, a new form factor. Officially introduced in revision 1.2 of the COM-HPC base specification. So right after this track, I hand over to Christian, so don't miss his track. He will continue with some insightful application examples. And yeah, let's have a look on the details. So what you see here, all right, here we go. So let's have a jointly look on how COM-HPC Mini compares against other computer module standards. So as a quick orientation, so each column represents one computer on module form factor. So on the left-hand side, COM-HPC client, followed by COM-Express Type 6. In the middle, our shining star of today. And last but not least, COM-Express Type 10, alias COM-Express Mini. And on the right-hand side, it's Mark. So let me put some details here. So don't getting shocked by all the details listed here. This is a comprehensive comparison table across all named computer and module standards. So we will go quickly through it one by one. And yeah, let's start with the first column. So all in all, we have a single connector on the module, so not two, so just one connector. So we have a single 400-pin module connector, if we've learned already. So it's basically the same what we are using on the client and on the server type. Its pinout has been adapted from COM-HPC client, but it's not exactly meeting this pinning. So it has some modifications that's super important to mention today. The I/O voltage level has been changed mainly from 3.3 volts to 1.8 volts. In total, we have 16 PCI Express lanes up to Gen 5 speed, grouped in 3 sections. We are going to have a more detailed look in a couple of slides towards this topic. 2 of these lines are pin shared with optional SATA. Another 2 lanes are pin shared with HMI ports, so for additional Ethernet. Nowadays, a lot of applications require digital display interfaces. So we have on module 2 DDIs and 1 embedded display port. That's great. And more or less all applications nowadays require higher Ethernet speeds. So COM-HPC Mini provides 2 times N-base-T and optionally 2 times HMI ports, as I've mentioned already. In total, we have 8 super speed lanes. That's great. So with them, one can instantiate up to 4 USB4 and respective Thunderbolt, and of course DDI and USB 3. First time in history, we've standardized functional safety as well, and at 1.8 volt signal leveling. So this really makes COM-HPC Mini future-proof in this direction. COM-HPC Mini supports PCI Express target, so the other way around, and audio signals like I2S, SoundWire, HDA, essentially the same what has been standardized on COM-HPC client already. A lot of applications require camera connection, so we added FFC connectors on the PCB. So MIPC's I support in this regard has been predefined. So this helps to keep the camera cabling consistent across CPU generations and different vendors. So we have a straightforward SPI, ESPI, and SMB bus on the module. And first time we put CAN on the module. That's great. So it has been added to and it allows to enjoy, for instance, embedded CAN controllers of silicon. So that's nice. We have UART on board. We have GPIOs on board. So the same amount like we are enjoying on COM-HPC client, but then again on 1.8 volts level. We have a wide range power input ranging from 8 volts to 20 volts, allowing approximately 107 watts at 8 volts. The footprint is relatively small, so 95 by 70 millimeters for the PCB. And we have 2 options for the standoffs. So this makes this module very ideal for space-constrained applications. So it can be super flat and super small. On the remaining slides, I'm going to highlight 3 aspects more in detail. So it's speed and density, first of all. Secondly, electrical design power. And third, that it allows super compact designs. All right, so let's start with speed and density. So COM-HPC Mini simply gives you more. So with regards to PCI Express, 16 lanes up to Gen 5, as I've mentioned already. So that's a lot. So and these PCI Express interfaces are grouped in 3 or separated in 3 independent groups. One group is group 0 low A. This is ranging from PCIe 0 to 3, group 0 low B from 4 to 7, and group 0 high from 8 to 15. Each group has its own PCI Express reference clock and corresponding clock requisition signals. SATA, if one implements SATA, it needs to be filled at SATA 0 first before SATA 1, and the same principle applies to HMI when it comes to additional Ethernet interfaces. So, and there's a filling order. So at group 0 high, lane 8 to 11, one should use it first for NVMe. Then for the second NVMe, one should use lane 12 to 15. And for PCI Express graphic cards, for instance, or in general high bandwidth uplinks, and for accelerators and so on and so forth, one is using PCI Express 8 to 15. It is super important to highlight that in any case, if there's higher bandwidth available, so direct attached PCIe interfaces with higher bandwidth, they should, with priority, should be assigned to group number 1 high. For example, if a chipset, for instance, exposes PCI or supports PCI Express Gen 4 and Gen 5, the Gen 4 links would get the Gen 5 links would get priority assignment to group 0 high. Very important, on the COM-HPC Mini, it was decided to move the AC coupling caps on PCIe 0 to 7 fully off module, while on PCIe 5 to 15, the coupling caps allocation stay on module. Let's have a look on the on the USB or Thunderbolt interfaces. So the COM-HPC Mini multiplex up to 4 USB 4, up to 2 DDI ports, and up to 4 USB 3.2 signals, as described in this table. So at the moment, it's expected that the first 3 configurations will be the most popular. I invite you to remember that USB or each USB 4 and USB 3.2 port requires USB 2.0 to support functions, these functions. So this is defined in the USB specification. So, and the remaining USB 2.0 resources should be assigned to, or are the is port 6 to 7, and the port 0 to 5 are matched to the USB 4 and USB 3 signals. Important again, a quick side note from the technical angle. So USB 4 and Thunderbolt retimers implement DisplayPort auxiliary channel coupling resistors on the retimer ICs itself, and these parts are placed on the carrier board and not on the module. Let's have a look on the Ethernet part. So the COM-HPC Mini supports 2 N-base-T ports. So it's important to mention the difference to COM-HPC client here. So the N-base-T on the Mini, it is on a different connection, so the on a different pinning. Background, the second N-base-T port on the client was on connector J1, but due to the fact that this is simply not existing because we only have one board-to-board connector, it has to be relocated to another pinning. The Ethernet magnetics shall be implemented on the carrier board. That's clear. As a general playbook, all CPU modules shall have at least one 1G Ethernet port. In general, the Mini does not support any Ethernet KR interfaces. But one can add up to 4, so 2 N-base-T and 2 based on SGMII, but multiplexed with PCIe, of course, on lane number 2 and lane number 3. As a side note, again, to keep this coupling resistor thing in mind, note that the Ethernet SGMI signals have no on-module coupling caps. All right, let's have a view on another detail of COM-HPC Mini. So it offers high performance with less compromises. So on the left-hand side, you see all commonly used computer on module standards sorted by size. And on the right-hand side, you see its electrical design power available to power the CPU, the main memory, mass storage, and other peripherals provided by the module. The COM-HPC Mini ideally bridges the gap between the bigger and the smaller modules with providing more headroom to power all available flavors of, for instance, the typically available 45-watt class and VGA package when it comes to our x86 CPUs. But at the same time, it's nearly as compact as COM-Express Type 10 or COM-Express Mini and Smart, while providing really future-proven high-speed interfaces such as 10G Ethernet and PCI Express speed up to Gen 5. The COM-HPC Mini power domain and the ground pin assignments are different compared to the client. So a few pins has been reduced to offer more IOs on the 400 pins. But all in all, it still delivers 100, or it's supplied by 107 watts at 8 volts in worst case. So that's enough to really power even more demanding silicon flavors than typically available on Type 10, for instance. All right. Let's have a look on its footprint. So as indicated in the previous slide, COM-HPC Mini combines both. It's super compact and it provides high performance interfaces. So it's relatively compact compared to other form factors. It's very well illustrated here. So the bright green part in the figure shows the COM-HPC Mini compared to the other COM-HPC form factors. Important to notice the mounting hole paths for the Mini highlighted here in light green. And the other mounting holes are shown in gold. As you can see, there's a difference. So meaning it's from the mechanical point of view, it simply doesn't fit, which is good because we have conflicting pin assignment here. All right, let's not just have a look on the footprint, let's have a look on the third dimension too. So what you see here on the left is the COM-Express compared against COM-HPC Mini on the right when it comes to the thickness of the design. So COM-Express has 5mm and 8mm standoff options, plus additional 13mm for heat spreader. And COM-HPC Mini has 5mm and 10mm standoff options, plus additional 10mm heat spreader. As you can see, we can expect, first of all, more performance, while at the same time reducing its stack-up height by another 3mm compared to COM-Express and 5mm compared to COM-HPC client. All right. I hope you enjoyed this quick introduction to COM-HPC Mini. I would like to seamlessly hand over to Chris, who's going to provide some very insightful application examples, so that the specification becomes a bit more touchy and that you can imagine how one can use, for instance, all those rich interfaces and its compact size. All right, Chris, over to you. Thank you.
Thank you very much, Richard. Welcome, everybody. My name is Chris Engels from Product Marketing Manager, and I've collected some brief application examples just to visualize how COM-HPC Mini could be used in the industry. I apologize, these are really high-level views on how things could be decomposed. I know the world is much more complex and systems are much more complex, what I'm showing here, but as I said, this is just for giving people an idea of why COM-HPC Mini could be a good fit. My first example is about HMI platforms, so human-machine interfaces. They are typically having a display or come as an IPC, an industry PC, as a thin client or mobile handheld and such. And you find them everywhere, industrial productions, in automation, logistics, medical equipment, or in automotive applications, for example, heavy machinery. Typically, you need some scalability of the functionality and the performance, and very typically, people would mount the electronics behind the display itself, making it a compact platform. That also comes together with a requirement for that space is limited, cooling could be constrained. There might be rugged environments like in automotive applications, and those devices are designed for the application, so then water protected or suitable for medical certification. So whatever is applicable for the application here. In common is this sort of building practice here, display combined with the compute platform underneath. Depending on the application, there's some specific user interface on the screen or on keyboards and application software. I'm not digging into that. That set by the application itself, but obviously one will need a set of interfaces in order to accomplish the job here. Typically, there is a display either very closely connected to the electronics, so you could use EDP, DisplayPort, or HMI interface for that. If you have a separate display unit, then, for example, USB Type-C might be an appropriate interface to connect to that display. You would end up with touchscreen, keys, even a keyboard or joystick in order to control the software manually. Here, USB might be a suitable fit for interfacing those kind of devices. And then you certainly have some sort of network connections into, say, in a production environment or such, or field bus options in order to control specific machine elements. You may have need for access for digital and analog I/O or PCI Express connection and such. And if we put that down on a COM-HPC Mini platform, nice thing about computer on models in general is that there's already a lot of interfaces falling out of the compute platform on the module itself, and that's certainly also true for COM-HPC Mini. So there's typically PCI Express network connections, USB interfaces, and display interfaces available, and those can be routed down to the carrier, and then they are appropriately adapted to the application. For example, USB-C is not falling out of the module itself. It's basically USB 3 or 4, but on the carrier you convert it into a USB Type-C interface in order to connect it to the outside world. I mean, this makes it a very compact solution based on COM-HPC Mini, as the form factor is quite attractively small, but still large enough to give sufficient performance for the application, which requires this kind of performance level. In my next example, this is also more or less about automation. I want to talk about autonomous mobile robots. You find these devices in production warehouses, logistics, or in hospitals, and I'm pretty sure there are other examples where they are used. And their purpose basically is to carry pallets, boxes, goods, and they may have some optional mechanical help like forklift function or robot arm. And I mean, they're very similar to what has been there for the last couple of decades called automated guided vehicles. But those AGVs, they actually need some sort of wiring in the ground in order to find their way. The autonomous mobile robots, they are just autonomous. They can find their way themselves. They have probably stored maps inside and routes, but they also have additional sensors like cameras or laser scanners or tactile sensors in order to find their way through difficult terrain and maneuver around obstacles which lay in their path ahead of them. And they need to prevent any dangerous situation and protect people and prevent any sort of damage which could occur while maneuvering. So this requires some sort of intelligence on board, either AI-based or some other intelligent routing algorithms, and together with the sensor information that actually makes that autonomous functionality available to the machine. And basically, that's not only calling for interfaces, but also for sufficient amount of performance in order to accomplish the task. And once again, we decompose this into an example platform here. You would have to have access to the machine over a user interface. That would be, from a physical perspective, would be a network connection, a wireless network connection, certainly. And then you have various different types of sensors which are necessary in order to maneuver a device. So cameras, radar, a laser scanner may be necessary for reading barcodes, find the object which needs to be carried, and probably for additional protection, also tactile sensors. And then there's certainly electronic or engine devices, motors and such in the machine, batteries. So you have to have some sort of machine supervision sensors, which are also required. And GPS may be an option in some of the applications as well. And then you need to control everything. So the motors and gearing and robot arms and such that needs to be controlled by the platform itself. So it's a mixture of identify the environment, moving stuff, and making decisions all on the same compute platform. And then we once again can put this on COM-HPC Mini platform. So we have a carrier which provides all the necessary interfaces to the sensors, the antennas and storage, and probably field buses going to the various motor drives and such. And the nice thing about COM-HPC Mini here is it is sufficient enough from its say from its physical perspective and to provide a decent amount of compute performance and AI capabilities for such kind of task. In my last example, I mean, it's somewhat related to my previous example, but this is it's also a moving object, but it's a drone. And I mean, there's different sorts of drones, but we're speaking about professional drones here for, say, for transportation, surveillance, and mapping purposes. And if you look at the applications, there's just a huge ton of application examples out there, including farming or energy sector or any kind of research tasks which you can think of, and certainly different kinds of civil and fire protection or search and rescue. You name them all. And typically you have a remote control for a drone, but also you might have a desire to have a semi or fully autonomous operation capability built in. And then you have three groups of tasks which this drone usually perform. So it's either identifying something on the ground, the movement, people, objects, then detect something which is should not happen, like a leak in a gas pipeline, or measuring the topology on Earth, for example. So what we need to have here is some sort of airborne controller, which is identifying the environment of the drone, controlling the drone and its flight, but also supervising the various instrumentation and measurement data which comes out of the various sensors. And sensors can be, once again, can be cameras, infrared sensors, radar, and specifically in drone applications, radar is widely used for different purposes because you can actually tailor its specific tasks like distance or velocity measurements and navigation, but also for gas detection or other measurements. Yeah, and once again, deploying that onto a platform based on COM-HPC, it's very similar to the AMR. So you have a user interface over a wireless network connection, probably different sorts of interfaces, and depending on the application, different RF based technologies here. And then you have a huge range of sensors which are required to enable the capability to fly and move inside the air autonomously, but also to have the application-specific sensors for measuring something on the ground or in the atmosphere. You need to have some gyroscope capabilities, probably a GPS, And then certainly also you need to know what the machine status is on this type of vehicle. And you need to control a lot of things, motors, throttles, flaps, depending on the way this aircraft is designed. And if we put this down to COM-HPC, we once again find COM-HPC is quite suitable for this kind of task because it provides all the basic elements for connecting high-speed data sensors via PCI Express, for example, or via network. We have the USB capabilities built in, which also allow us to go, for example, to LiDAR or to go to a gyroscope, because these are standard interfaces in these areas as well. COM-HPC provides the real estate for providing sufficient performance based on AI technologies and other compute capabilities in order to map the application and autonomous function onto the module. And depending on the size of the drone, you also may have requirements like no power consumption, weight and space constraints, which nicely fit to the way COM-HPC has been defined. So these are 3 examples. I'm sure there's tons of examples out there. I've tried to pick some more here, just an example. So in multimedia applications, 3D visualization, for example, or medical medical and life support equipment or test equipment, which can be carried in other applications, COM-HPC is a good fit. In general, applications that require a scalable compute performance have sufficient or that needs sufficient amount of I/O connectivity and bandwidth that require a compact form factor on a low weight at moderate power consumption. I think then COM-HPC Mini is a really good fit here, beside the other computer on module standards which are on the market today. And with that, I give it over to Bren. Thank you.
Thanks a lot, Chris. That's awesome. A lot of good stuff there from both Richard and Chris. We really appreciate that look into COM-HPC Mini and what you're going to be able to do with it potentially in the coming years and hopefully decades. So now, talking about what you're going to be able to do with it, we're now going to jump into the COM-HPC design guide. So there's been an update to the carrier design guide, which is what you use to have tips for building the companion carrier board for the COM-HPC Mini and other modules. So that session is going to be taking place at the link on your screen here in about 3 to 4 minutes. I'm going to jump over there, get everything fired up, and join up with Peter Hunold, who's going to walk us through some tips there. So we'll see you on the other side. Thanks so much, Chris and Richard, and keep watching.